Okay, hello everyone. Today we are going to take a look at operational amplifiers or op amps. And this is the circuit symbol for an op amp. It's just a triangle. It takes two inputs and one output, V out. And the thing that you have to remember for our purposes is an op amp, the currents are approximately zero going into this into the configuration right here, and yes, going into the configuration here, and this current is also zero. But the most important thing is that V1 is equal to V2. Okay, I'm not sure why, but there's a bunch of circuitry that goes on in here that's beyond me and beyond this course. And what it does is it amplifies this current right here. Okay, so let's just get into a few configurations of op amps. So the first configuration is an inverting op amp example. So basically what this does is it takes this VI right here and it inverts it, right? So then this becomes some ratio of these resistors, but negated, okay? And we're gonna go ahead and prove that. So in solving these op amps, and just as a disclaimer, this is a super high level view of op amps. We're just gonna mechanically look at how we calculate voltage of it. We're not gonna look at exactly why it does what it does, why it amplifies signals and stuff like that. We are just going to simply calculate the voltages, and yes, the voltages. So we're going to have two nodes right here, and we'll call this one node 1, and we'll call this one node 2. And remember what we said before, that V1 is equal to V2, right? And so there's a forcing there's a forcing, I would say, voltage at N2, and because it's just 0 volts, it's connected directly to ground. And if this is 0 volts, then this right here must be 0 volts as well. Okay? And we're going to apply a simple nodal analysis to find it in terms of V naught. And notice that for this lesson, we are not going to be using numbers. We're going to be using just general R for resistor, V for voltage. So we're going to look at this very analytically. So we're going to go ahead and write our nodal analysis for N1, and we will have 0 minus VI over R1 plus 0 minus V out over R2 equals 0. And we want to get V out all by itself because that's what we're looking for. So we're going to multiply both sides by R2, or both sides by R2, and we're going to get negative R2 R1 VI minus V naught equals 0. And we will notice that we get V naught is equal to negative R2 R1 VI. And so as you can see here, whatever the voltage was in going into this negative side of the op amp, it would become some factor, it would be multiplied by some ratio of R2 to R1 and be negated, okay? And that would be V naught. So if VI was a negative 5 volts and R1 was 2 ohms and R2 was 10 ohms, then our V naught would be amplified by times 5, right? Because 10 divided by 2 is 5, and it would be negated because it would be a negative, so it would be negative 10 over 2 times -5, and V out would be 25 volts. Okay. Now let's take a look at the non-inverting op-amp example. And this time, the battery is actually on the positive portion of this op-amp. And we're going to do the same thing. We're going to have a node here and a node here. I'm going to say this is node 1 and this is node 2. And now node 2 has VI at this part right here. And so VI, this node right here will also be VI. Okay. And so we're going to go ahead and solve our nodal analysis at node 1, and we're going to say VI minus 0 over R1, right, plus VI minus V naught over R2 is equal to 0. Now we're going to go ahead and simplify this and solve for V naught. We're going to multiply both sides by R2, and we're going to get R2, R1, VI plus VI minus V naught equals 0. We're going to go ahead and add V naught to both sides, and then we're going to take out the VI. Okay, so V naught is equal to VI taken out 1 plus R2 over R1. And so when you multiply, what this result means is that whatever the input voltage is, it will be multiplied by a factor of 1 plus R2 over R1, and that will be our V naught. And once again, it's another amplification, but we don't need to put a negative voltage in if we want to get a positive voltage. Okay? And now we are going to go ahead and take a look at an adder configuration. So in an adder configuration, the voltages are added. So we have two voltage sources right here going into this negative side right here. And we are basically going to perform another nodal analysis. So we're going to draw our node here. We have a node right here. And that's going to be N1, or we'll call it N2 to be consistent. And this one is N1. And both are 0 volts. Okay. And now we are going to solve for N1 once again. N1, 0 minus V1 over R1 plus 0 minus V2 over R2 plus 0 minus VF over RF equals 0. Now we're going to go ahead and move VF over to the next to the other side. So VF over RF is equal to negative, and I'm going to go ahead and take out this negative right here, V1 plus V2 over R1 and then over R2, and we will get VF, or rather V naught, I don't know why I called it VF, V naught, or V out rather, V out is equal to negative RF V1 over R1 plus V2 over R2. And just for the sake of it being an adder, like a pure, voltage plus voltage adder, we will have RF equal R1 equal R2, so that everything cancels out. And so we get V naught is equal to negative V1 plus V2. And notice here that it's been negated once again, okay? Because we put it at this portion right here. Now, if you put it here instead, the added configuration, then you will be able to add and invert it. But the coefficient will be different. It will look something like this. And so I would encourage you to go and try that yourself and see and figure that out, mathematically. But as you can see here, if you have both of the resistors being the same, then you can get a full, like a complete addition of the voltages, but negated. Another thing that you might notice is that this RF right here, it is responsible for the amplification. Okay, so this guy right here is necessary for our op-amp circuits. Okay, we're always going to have something up here and right here. And for our last configuration, we have a subtractor configuration. Okay, once again, we have a top amplifier, and we are going to write our nodes. N1 is V1, and then N2 is V2. And we are going to write the nodal equation for N1. We are going to have, sorry, this is not V1, this is V2. We will have V2 minus V1 over R1 plus V2 minus V naught over R2 is equal to 0. And we will just simply solve for V naught. Multiply both sides by R2 over R1, V2 minus V1 plus V2 is equal to V naught. And as you can see here, there's already a subtraction right here, plus an initial V2. And under the premise that R2 is equal to R1, we will get V naught is equal to 2V2 minus V1. While this is not a complete subtraction like it was here as being a complete addition, we do get a subtraction of these voltages. And I'm sure that there's a different way, there's another way, or some kind of configuration by which you can get a full subtraction of these two voltages, but I'd encourage you guys to figure that out. So that's it for op amps. One more thing I want to highlight is the fact that you are not going to draw a node at V naught. Okay, that is just a mathematical thing. Like just don't draw a node here. It'll greatly simplify. You're just adding an additional node to your equations for no reason. Okay, so we are going to, in the next lesson, solve some more complex op-amp circuits, and you will have to do like nodal analysis at different portions of this in different configurations right here. And that will be it for unit 2. And in the next unit, we will be solving circuits with capacitors and inductors, and that will require knowledge in differential equations, but we will walk through each problem step by step like we have been currently. So hope you guys enjoyed the video, and I'll see you in the next one.